Okay, so shafts are there to transmit energy, transmit torque. So we're going to need to do that somehow. Not just uh, getting the torque down the shaft, we also need to get it off the shaft. So onto some sort of gear, maybe onto a propeller, onto or from an engine onto wheels. So you need to have some sort of thing that connects the torque, connects the shaft to whatever is supplying the power or whatever is using the power. So one of the most common ways of doing this is with a key. So basically, you cut a groove into the shaft, you cut a groove into the component that you're mounting to it, the hub or whatever, and you stick a piece of metal inside the gap there. And then basically, as the shaft tries to rotate around, this face here is going to press against the key, and then stress is going to get transmitted across the component, and then this face of the key here is going to press against this face of the component mounted, and then you're going to get your torque transferred. So again, most common of those is going to be a square key. We've also got flat keys, round keys sometimes, Kennedy keys, oriented like this, often tapered. Heavy-duty applications use those. Woodruff keys, automotive and machine tool industries use those. Gib head keys, those can be useful for locating it as well, because you can kind of hammer it on until it's hammer your component on kind of onto the key until it's at the right spot. Now we got feather keys. So those are keys that are basically screwed into the shaft, and these are designed for applications where where you want the hub to slide axially. We also have pins. So pins are often going to be used as points of failure. So if you want, if you know that there are instances where you could have some sort of overload occurring, like say if a propeller of a boat hits a rock, then essentially the pin could act, the shear pin here could act as a point that is designed to fail before anything else. So basically, if the propeller hits the rock, then you're going to get a sudden spike in the torque, and the relative torque between the propeller and the shaft. And then as a result of that occurring, the pin can break, and then the shaft will, the shaft will see a bit of a spike of torque, but once it then the pin will break, and then it'll kind of start spinning freely, and then basically it'll limit the amount of extra torque and extra energy that makes its way to the engine, preventing damage. So instead of breaking an engine that you paid hundreds or thousands of dollars for, you're instead breaking a shear pin that costs 25 cents. I don't know how much these things cost. I mean, it's a small bit of metal. I haven't looked into pricing lately, but it's still a hell of a lot cheaper than replacing your engine. So you can have straight round pins, tapered round pins, split tubular spring pins here, so those will be basically a bit easier to insert. Got groove pins, so those are basically allowing for allowing for retention of the pin a bit easier. For other mounting parts, retaining rings, also called snap rings. So these things basically are used to position a gear or what have you at a specific spot on the shaft, so it doesn't move back and forth along the shaft. So the conventional type here, those they fit in a groove that has been cut into the shaft. And we've also got push-on types. So these ones kind of just like the teeth here, they kind of bite in order to apply whatever force they need to hold that component at the right spot. So they're not going to be able to, as a result, they're not going to be able to have as much kind of holding force as you would with the conventional type, but they can be used in situations at spots along the shaft where your stresses are too high to really be able to allow you to cut a groove in. Because otherwise, cutting in a groove like that is going to act as a stress concentration factor, and that could lead to fatigue failure. Well, it's got splines. So splines they're kind of like built-in keyways. So basically, you kind of cut these teeth into the shaft and into the hub that you're fitting it on, and kind of just mount it on. So they kind of act, they may look similar to gear teeth, like an involute profile, or they could have other profiles too. But basically, they're kind of keys that have kind of been built into the shaft, basically. Those are used for applications where you're transmitting quite a lot of torque and you would otherwise have failure of the keys. They're good for sharing the load across the entire way as well. So as for loading, so we don't want loosely fit keys. Basically, we want kind of no vertical gap here at the top or the bottom to prevent rotation of the key. So nice tight fit at the top and the bottom. And then one of the primary methods of failure would be shear failure. So kind of failing across that way. Another type of failure that we could have is failure of the compressive failure of the faces. So on the shaft, we got this face here. So essentially, we're in order to transmit torque, we're applying a certain amount of force. So the amount of force that we're applying is a function of the torque that we're applying and the diameter of the shaft. And then what am I trying to say here? That force is shared across a certain area. So that area is basically going to be based upon the length of the key and the size of that face there. So that's and that should be half of h. So where h is the height of the key. That's h there. Now the most typical sizing for square keys is where we have an h of d over 4. So if we have an h of d over 4, then basically, if we have an h of d over 4, then we basically sub in d over 4 for here, and we end up getting sy times L times d squared over 16. Now, So basically, the calculations for the calculation is kind of the same depending, regardless of whether or not we're talking kind of this face here on the the shaft, this face here on the key, this face here on the key, or this face here on the hub or whatever it is, or the mounting component. What could change there, however, is the SY. So whether or not whichever one of them has the lowest yield strength is going to be the limiting factor for the maximum amount of torque that you can transmit based upon what am I trying to say here? Based upon based upon that loading condition. So the lowest of those three materials for this failure criteria. And of course, if you're told to have a particular safety factor, then obviously the maximum torque would be knocked down by that safety factor. So if you had a safety factor of 1.5, it'd be this divided by 1.5. The other failure criteria could be that you have the maximum amount of torque before the key itself starts to fail in shear. So not a compressive yielding failure, but a shear failure, kind of like that. So again, anytime you see 0.58 or 0.577, depending upon how many decimals they want to use of SY, that's basically us taking that's basically us taking a yield strength and tensile and converting it to the von Mises equivalent for a shear failure. So when that's going to be occurring, and basically, we're applying a certain amount of force. That force is based upon how much torque you have. So again, the torque is equal to the force times the distance. And then that force divided by an area, except in this case, it's an area based upon I did not mean to do that. Just in this case, it's based upon this cross section here and not that one. Keep hitting the damn wrong button. So anyways, in that instance, it is going to be the height times the diameter over 2 times L times the shear strength of our key material. And then in instances where our H is D over 4, then it works out to be this here by subbing in D over 4 for H. So, and again, that's just based upon failure for the key. So as opposed to the previous calculation where we're worried about the shear strength, the yield strength for all the metals. Here we're just worried about the yield strength for the key material. And again, count yours for your safety factor. And the other thing that was mentioned, just that you should keep in mind, it was mentioned when we're talking about the fatigue for the shaft. I think last lecture, the lecture before that, no, 2 lectures ago. It was the fact that anytime you cut a keyway into a shaft, it is going to act as a stress concentrator. So you're going to get some sort of decrease in the expected lifespan of your an increase in the apparent stress levels for your material. Now, here again, they skipped the whole finding a KT, then finding your notch sensitivity factor, and figuring out what your fatigue safety factor is based upon that. They basically just went straight to estimates of the fatigue safety factor for the different types of ways to cut a keyway. So whether or not using an end mill or sled runner to cut, and then of course whether or not the load is in bending or in torsion, and whether or not we're talking as a yield state or some sort of hardened material, quenched and drawn. And then some standard size keys that you could find available for different shaft sizes is listed here. So we could have different size keys for these sized shafts, and then the keyway depth that you would need to cut in order to get those is listed here. Not really sure why they bothered to list it, to be honest, because it's just the H here divided by 2. Honestly, I'm not sure why they bothered having a W as well, because they specified that these are for standards. Well, okay. Oh, no, yeah, never mind. So standard square and rectangular key applications. So they do have a few here that aren't square. Yeah, fair enough. But anyways, in any instance, the keyway depth is always going to be half the H here. So loading of pins. So as mentioned, pins are often designed to be the point of failure, shear pins. So we can figure out what sort of maximum torque that would occur based again upon the strength of the material for the pin, the diameter of the pin. So yeah, that's the diameter of the pin itself. That's the small d there, and then the diameter of the shaft. That's the big D there. Set screws. So the way set screws work is basically you take the component that you're mounting to it, you drill some threaded holes in them, and then often but not always you're also going to machine small flat surfaces on the shaft itself. And then basically you just insert the set screws into that threaded hole and tighten them up until they're pressing up against that surface, and then kind of just crank down on it. So you're gonna crank it down to a particular torque based upon the size of the set screw, and that's going to give you a certain amount of holding power. So basically the holding power is the ability for that set screw. So say we got the shaft here, got the set screw that's pressing into it here. If the shaft's going to want to rotate, basically the holding power is going to be the maximum force that is going to be used to transmit the torque. So the amount of torque that you can transmit using the set screw is going to be a function of the holding power and the radius of the shaft in question. Other things you might see: press fits, shrink fits, or similar idea for bonding. So basically we're ramming the shaft into a hole in the thing that we need, into, and then we may just be forcing it. We may be using thermal expansion to basically we can cool down the shaft, we can heat up the outer component until they fit in, and then allow it to return to equal temperature, and then the outer component will be clamping down tightly upon the inner component and upon the shaft, and that'll allow for transmission of quite a lot of torque because that clamping force is quite high. So there's going to be quite a lot of friction. And again, you can add some bonding agents in there as well to kind of increase the degree to which that's the case. Minimal stress concentration. That having been said, especially for shrink fits, that clamping down action that's going on, you're generating a fair amount of stress as you're doing it. So you're getting a fair amount of compressive stress on the on your shaft, and you're getting quite a lot of tensile stress going on in your outer component, your gear, or your whatever it is that you're attaching it to. Couplings, on the other hand, aren't used for connecting shafts to things that use the power. Couplings are used to connect shafts to other sections of shaft. So, I mean, if you have, say, a shaft that runs from the forward engine room of a Halifax-class frigate back to the propellers, you're not doing that one piece. So you're going to need some sort of coupling in order to connect those two shafts. It'll connect multiple segments of the shaft together. So one way of doing that is rigid coupling. So basically, you have a coupling here that's got a flange going on. So you're going to be the torque that you can use is limited by basically the whatever it is that you're using to connect the coupling to the shaft. You're limited by the web or the strength of the web portion. So that's this section here. So essentially, as the thing tries to rotate, then let's see. We got holes there. So basically, as this thing is going to want to rotate, we're also going to have bolts in those holes. So basically, this segment here is going to press into the bolt, and then the bolt needs to transmit the torque to basically its counterpart on the other side. So we could get some yielding in this web portion here, and then the strength of the bolts as well often also comes into play. So this may just end up being you saying, "Hey, I need more bolt holes." So you're not going to have a rigid coupling that has one. At the very least, you're going to have enough to be symmetrical. But there's rarely any reason to use less than 4, I'd say. So rigid couplings are useful for collinear shafts, so shafts where the center lines of the two shafts are properly aligned, both in position and in angle. Flexible couplings can be used to accommodate some slight misalignment. So they basically all use some sort of rubber elements to attain a connection. So basic shear type coupling here. It's got the rubber there. It's you bond the rubber to each shaft, and then basically it just as it tries to rotate, you get a kind of shear loading situation going on that passes the torque from one to the other. Heavy duty type couplings here. So we get basically kind of like this flange here with this connection here that it is able to kind of bolt down and clamp onto this rubber gasket here. I guess it's not really a gasket. Rubber coupling, I guess. So it's able to able to hold on tightly to that. It's nice, nice and heavy duty connection, while still allowing some some connection, some slight flexing going on there. This constant stress, constant strain one is interesting. So you'll recall that basically the strain in a torque loading situation varies linearly from the center of the uh, from the center of the axes about which the torque is acting. So this one basically kind of accounts for that by increasing the cross section of the rubber coupling that is being loaded up, such that the strain, like the strain across the entire thing, is constant as you increase your in radius. So it allows, basically makes sure that you don't have some massive concentration of shear stress at the outside while the stuff in the middle isn't doing anything. We got Oldham or slider block style couplings. So these are allowing for some degree of misalignment, positional misalignment. So, something like this. It'd be allows you to basically still be able to rotate while misaligned in position. Doesn't necessarily allow for misalignment in angle. But they rely on basically having a slider block in the middle that is able to kind of move back and forth in these grooves. And and basically kind of even with the misalignment, as it rotates, the slider block moves back and forth and is still able to transmit the torque. So again, you get more sliding the greater the misalignment is, and the one of the issues is that obviously because of that sliding, you're gonna be generating, you need to account for the friction. So lubrication is key for reducing friction, but you're going to get some wear going on. You're going to be generating heat. You're going to be wasting some energy. So basically, as a result, some of the not all the torque's going to make it to the other side. You're going to be wasting some of that energy that would have otherwise been a useful transmission of power, just going into heat, basically. So I'll show you. I'll provide a link in the comments that has a good example of how one of those is working. And finally, we got a universal joint. So universal joints, those are the ones that allow for misalignment of the angle. So they got this yoke thing in the middle that allows for they got this yoke thing in the middle that kind of is able to rotate in between the two sides, and basically it allows for the passage of the rotation allows for the transmission of the rotation from one shaft to the other with the misalignment. One of the issues is that when you do have a universal joint coupling at a particular angle, the input speed changes as you rotate. So it's not going to be constant. That having been said, that can be taken into account. So basically, if you, how do I say? If you have an angle, one angle and another one, and then kind of shift back then as long as these two angles are the same, you're kind of going to be with the second addition of another universal joint at the same angle, it's basically gonna trans the first change in the speed as a function of angle is going to cancel itself out. So you can maintain a constant input and output velocity speed by using two universal joints at the same angle. So again, in the comments, I will post a video that kind of goes over that a bit more, because again, this is one of those ones that's kind of hard to describe without seeing it in action. But that is it for now. So that's it for the theory portion of the shafts that we'll be doing. So I'll be doing some examples next week, and then your assignments due the week after, the Sunday after that. All right, see you guys.